Hi everyone, and welcome to part 2 of this series where we are solving DC circuits. And yeah, in part 2, we're actually looking at questions that are a little bit more complicated. And so I'll walk you through them. Let's see, in question 1, we have a battery, 18 volts, and it's connected to resistors. So these two resistors, 12 ohm, 3 ohms, and also a 9 ohm resistor. And part A asks what is the effective resistance. So if I want to combine all these resistors together, to find the total effective resistance. What is it? What would it be? And part B asks, what is the current flowing through the 12 ohm resistor? What's the current going through? So let's just look at part A first. What is the effective resistance? And over here you can see, let's look, when we try to simplify resistors, we always look at the one that we can apply the formula to most straightforwardly and most simply. So if you look at this, let's say if you wanted to apply any formula, you look at these two resistors. It's kind of complicated because even if you want to use the parallel formula, you have this resistor kind of in the way, right? So it's not straightforward. But how about these two resistors? It's very straightforward. It's very clear that they are in series. So actually, let's do that. Let's basically redraw this circuit to look like this. We're actually simplifying the circuit. And if you're not familiar with this process, please go look at part 1, and I think it'll be clearer. And so that's what we're doing over here. So this resistor is actually 12 plus 3 because of the series formula. We add them up, and this is actually 15 ohms. Of course, this remains as 9 ohms. Yep. And then now that we have these two resistors, they are very straightforwardly and clearly in parallel with each other. So we can continue to simplify this circuit to look like this. And what is this? This is actually the total effective resistance. And let's try to calculate that. Applying the parallel formula, because these two are in parallel, we can see that 1 over the effective resistance will be equal to 1 over 15 plus 1 over 9. And then we continue to simplify. Then when we key into our calculator, we actually get 8 over 45. And then we can just flip the fractions on both sides of the equation. That's what we get. And this simply gives us 5.625 ohms, and if I want to put it to 3 significant figures, this would be 5.63 ohms. There we go, part A. Okay, right now, let's look at part B, and part B says it asks for the current flowing through the 12 ohm resistor. And so if we try to analyze the current, we see that, okay, this is from the battery, positive, negative, so current flowing out. Over here, you can see the current splits. There's some current going through here, and some current continues to the 9 ohm resistor. Of course, the current going through the 12 ohm resistor goes here, and it recombines here to give the total current, which goes back to the battery. And so let's think about it. We want to find the current, so we probably are going to use V equals to IR at some point. And if it's a 12 ohm resistor, we can ask ourselves, can we use V equals to IR across the 12 ohm? In that case, we will need to know the resistance. So let's just brainstorm a little bit. Let's say V equals to IR. And so we will need to know R, which is 12 ohms. We don't know I, but we can solve for it. We need to know V, which is V across the 12 ohm resistor. But do we know this V? Actually, we don't. We actually don't, because if you analyze, and maybe allow me to just write, if it's 18 volts, so I'll assign 18 here and 0 here. And if you haven't seen this before, please watch the previous videos in this series. 18 here, and over here is 0, we've assigned 0 all the way. Once it sees a resistor, then something is up. Since it's 0 here and it's 18 here, this must be some value, and we don't know, it's some middle value. So we actually don't know the voltage across the 12 ohm resistor. So what do we do then? So we realize we cannot just apply V equals IR across the 12 ohm resistor. But hey, do I know the potential difference across this entire chunk? Yes. It's actually 18 minus 0, which is just 18 volts. And do I know the total resistance here? Yes, I've already combined them actually in part A, where over here you can see I can actually combine them to give 15 ohms. So in that case, what I can try to do for part B is, let me write it here. Let's try to say that it's 12 ohms, this is 3 ohms, and the potential difference across it is actually 18 volts. And so let's redraw this as 15 ohms, and potential difference across it is 18 volts, right? You can see. And then what I can do now is I can find the current. So I can say V equals to I multiplied by R. Now you may wonder, hey, but isn't that the current flowing through like this section? Like, how could you guys combine the current? The thing is, then we realize that because these two are in series, the current flowing through the 12 ohm is the same current flowing through the 3 ohm, and it's the same current flowing through this whole wire. Is basically the same current. And so it doesn't matter if we combine. Yeah, it doesn't matter if we combine it, because actually what the battery sees, the battery doesn't actually quote unquote see a 12 ohm and a 3 ohm. It actually sees the resistance, total resistance here. It sees like 15 ohms. And based on that, it sends out the current accordingly. And so, well, if I'm using layman terms, so actually this is in some sense what the battery sees, because it's giving a potential difference of 18 volts across this whole chunk. So when it sees 15 ohms, it'll be like, oh, 18 volts, 15 ohms. Okay, this is the amount of current that I will send out. So, yep. And so the current, in this case, if we continue to simplify, it will be 18 divided by 15, which gives me 1.2 amperes. And there you go. All right, and let's look at question 2. We have another circuit now, 24 volts for battery, and then we have resistor A, resistor B, C, and resistor D. And each resistor, we've been given the resistances of each resistor. Okay, part A, which two resistors have the same current in them? Okay, quite straightforwardly, this is a question that actually doesn't require much calculation. So let's analyze the current. The current flows out, right? Positive, negative. It flows through the resistor A, and then over here it splits. It splits. So maybe let's call this I total coming out. So I total is going through resistor A. Over here it splits. Let's call this IB because it's the current going through resistor B. And let's call this IC because it's the current going through resistor C. So IB and IC, if you look at the parallel circuits video, IB plus IC will give me IT, which is I total. And then when they combine back, it gives me back IT. So I cannot just lose current, right? The current has to be conserved in that sense. If I started with this amount and it splits up, and then when I recombine back, it has to give me back the same amount of current. And so IT goes in all the way back. So immediately we can already see which two resistors have the same current in them. Resistors A and D, which is IT is going through both of them. Okay, part B. Which two resistors have the same potential difference across them? So for this part, let me just color code it. 24 volts, you know I like to label 24 and 0. And so remember, the potential doesn't change until it goes across something with resistance, and 24 remains here. Okay, now it's going to go across something, and so it's going to be some value lower than 24. And so for simplicity, let's just call this value X. And you can see that because the wire has no resistance, it's going to be X X all the way. And on the right hand side, you see it's 0, 0, 0, 0. It's going to be 0 until it reaches the resistor D. And then it's going to be some value over here that's a bit higher than 0. And let's just call this value Y. And so it's going to be Y. And the Y has no resistance. And Y all the way. Immediately, you can see that the potential difference across resistor B is going to be X minus Y. And the potential difference across resistor C is also X minus Y. So immediately you can see that resistors B and C will have the same potential difference across them. And now let's look at part C, which asks for the total effective resistance. And we can see that, let's look at the most simple combinations of resistors first, and we simplify from there. So immediately we can see that these two are in parallel with each other with no complication. And so really, I think what we should do is we should simplify the circuit to look like this. So we don't touch the 14 ohms yet. And we simplify these resistors B and C. So let's call this R BC. It's basically the total resistance from resistors B and C. And of course, this is 12 ohms. We don't touch it either. And to simplify, let's find that it's 1 over RBC, because they are in parallel. It's 1 over 12 plus 1 over 6. And so this gives us 1 over 4. And so RBC is basically 4 ohms. And so we can say that this is actually 4 ohms. And then now we can see that all three resistors are in series with each other very simply. So we just add it all up. And so that's straightforward enough. So this would give R effective. So really we are simplifying the circuit to look like this now, which is R effective. And this is basically 14 plus 4 plus 12. That gives me 20 ohms. So this is 20 ohms. There you go. All right, and now let's look at part D. And for part D, they're asking for the current going through resistor D. So we're asking for this current going through resistor D, which is actually the total current. It's actually the total current. So if you want to find the total current, actually it's not that complicated because we've already simplified the circuit to look like this. And this is still 24 volts, am I right? And so if this is 24 volts and this resistor, total resistance is 20 ohms, I can find the total current. So what I can say is V equals to IR for the total effective resistance. And so V is 24 volts, because just to clarify, it's 24 and 0 here, and so it's still going to be 24 and 0 here. Potential difference across the effective resistor is 24 volts. And I is the total current, and R is 20 ohms, the total resistance. And so I total is 24 divided by 20, which actually gives me 1.2 amperes. And then you see that I total, because the question asks for ID, I total is ID, and so I total, or should I say ID, is basically the I total, which is 1.2 amperes. You're done. Finally, for this last part, we are looking at the voltage across resistor A, right? Voltage across resistor A, and so you're looking for the potential difference across. So really, we're trying to find, in some sense, what is 24 minus X? What is the difference, potential difference across it? It sounds complicated, but actually it's not, because you can already see that we already know what I total is. I total is 1.2 amperes. So the current going through resistor A is 1.2 amperes. That's I. And so we can say IA is 1.2 amperes. And the potential difference across A, we don't know. Do we know the resistance of A? Yes, 14 ohms. there you go. You can apply V equals to IR and solve for V. So let me just do part D here, since all the working is here. And so V equals to IR gives me VA equals to 1.2 amperes times 14, and that gives me 16.8 volts. So the potential difference across it is 16.8 volts, and you're done. And allow me just to clarify a little bit. Potential difference across A is 16.8 volts. So what is X? So the difference actually is 24 minus X equals to 16.8, because you'll be connecting a voltmeter across it. So the voltmeter will say, 24 on one side, and then it reads X on the other side. And when it gives me that difference, it is 16.8. So X really is 24 minus 16.8, which is 7.2. So you will only have to do that if, let's say, you wanted to go even further and try to calculate and solve for things relating to resistor B and C. But in this question, we don't go there. So it's not that complicated.